Hello grade 10s and welcome back to this series on particles substances are made of. In our previous lesson we studied metallic compounds. We saw that metallic compounds have their atoms arranged in a crystal lattice. In today's lesson we will compare the metallic lattice and the lattice formed by solid ionic compounds. The positive nuclei of the metal atoms are held rigidly in the lattice, while the electrons that surround the nucleus move freely throughout the lattice. These delocalized electrons explain why metals are such good conductors of electricity. Let us refresh our memories about the structure of the metallic lattice. As already mentioned, metals form a lattice when they are in the solid phase. A lattice is a regular, repetitive structure. In the case of metals, it is the positive nuclei of the atoms that are held firmly in the lattice and the surrounding electrons are free to move, making a sea of delocalized electrons throughout the lattice. Let us have a look at the ionic bonding model.
Now that we have looked at the metallic bonding model, it's time to move on to ionic bonding. You may remember that Gilbert Lewis contributed to our understanding of chemical bonding when he proposed the valence bond theory. He thought that only the electrons in the outer energy level, or valence electrons, are involved in forming chemical bonds, and so only these need to be considered when describing chemical bonds. This gave us a shorthand way of representing what happens when elements react together. Let's have a look at how he would have represented the bonding taking place when sodium reacts with chlorine. The Lewis diagram of sodium is the symbol for sodium, Na, with a cross, which represents one valence electron. Can you draw the Lewis structure of chlorine? Well, we start by writing the symbol for chlorine as Cl. And then draw in the 7 valence electrons as 7 dots. When these elements react together, sodium loses an electron to become a positively charged sodium ion. And chlorine gains an electron to become a negatively charged ion. There will clearly be strong electrostatic forces between these charged ions. That's why this sort of bonding is called ionic bonding. These Lewis diagrams are also models, but in this case, this model does not give us the full picture. This is because the transfer of electrons does not take place between a single sodium atom and a single chlorine atom, but takes place between many billions of atoms. These particles join together in a very ordered giant lattice. The smallest unit of this lattice is made up of 4 sodium ions and 4 chloride ions. 3, 4. This is called the unit cell. We use the unit cell to think about the special arrangements of the atoms and to determine the formula. In the unit cell, the ratio of sodium to chlorine is 1:1. So the chemical formula is written as NaCl. Even though there is never ever just one sodium and chlorine in a structure. In fact, the unit cell is repeated many billions of times in one tiny crystal of sodium chloride. This is a more accurate model of sodium chloride than the one provided by Lewis diagrams, but we will see later that even this model can be improved. You should recall that the same type of ionic bonds form whenever a metal reacts with a non-metal. The metal loses electrons to form positive ions, and the non-metal gains electrons to form negative ions. The ions are held together by strong electrostatic forces in a crystal lattice.
We've had a close look at both metallic and ionic lattices, so let us compare the two types of lattices. We will consider the similarities and differences between the two. The similarity between ionic and metallic solids is that they will both form lattices. The major difference between these two lattices, though, is that in the metallic lattice, only the positive nuclei are held in the lattice, while the electrons are free to move throughout the lattice. By comparison, both the positive and negative ions in the ionic lattice are held within the lattice and are not free to move. As a result, solid ionic compounds are not very good conductors of electricity. We have reached the end of today's lesson. Be sure to attempt the task video at the end of this series. You can also find out more information on this topic at www.mindset.co.za/learn. Join me in the next lesson when we will have a look at the next model of bonding and its lattice. Until then, goodbye.